This video is going to explore mathematical inverse functions. Before we talk about inverse functions, I want to talk about the inverse in general and the idea of the connection between inverses and identities. When we add things together, an additive inverse is like a negative number. So if I take 2 plus negative 2, these two objects are additive inverses. When I put them together, they cancel out. And the result is 0. Okay? So when we do this, we take a thing, the inverse of that thing, we combine them using the addition operation, and the result is 0. This idea works or is repeated for anything and any inverse of that thing. So I've added 2 and negative 2 and I've gotten 0, but I can change this to add x and negative x. If x is any real number and I add x and negative x, I get 0. So the idea of an inverse in general is to cancel things out. When I have an additive inverse, I use the negative, or when I want an additive inverse, I use the negative, and the result is 0. This 0 is the identity for addition. Okay? So an inverse cancels something out relative to a certain operation, and an identity is what you get when you cancel things out with respect to that operation. So for addition, the inverse is the negative and the identity is 0. For multiplication, suppose I have x times 1 over x. This is the multiplicative inverse. Okay. And the result is 1, and this is the identity for multiplication. Okay? So you take a thing, you combine it with an operation and its inverse for that operation, the result is the identity. This works for addition, this works for multiplication, and this idea also carries over to mathematical functions. But with mathematical functions, the objects are a little bit more complicated, so the ideas are more nuanced, they're more technical. All right, so what I want to do first is I want to define the identity function for you, and then I want to show you how a function and its inverse can combine to give you the identity function. So what identities do is they leave things alone. If I take the identity for addition and I add it to something, it leaves that thing unchanged. X plus 0 is equal to x. If I take the identity for multiplication and I multiply that by something, it leaves that thing unchanged. X times 1 is equal to x. And it's that idea that we want to carry over when we're defining the identity function. So if we're trying to define a function which leaves things alone, we know that functions take in inputs and return outputs. So if we're trying to define the identity function, what we would expect is, or a reasonable choice for that, might be simply to choose the identity function is equal to the input. That will leave anything that you give it as input alone. It doesn't change anything. It just kind of is passively allows that thing to pass through, to turn from an input into an output. So this is what we're going to use as an identity function. If we're trying to define an inverse, we want to combine a function and its inverse, and their combination should produce this identity function. So if I was thinking about combining functions, a natural way to combine functions would be to use composition. That's a way of layering them on top of one another. So let's define a simple shorthand notation for an inverse function. So let's say f is a function. So if f is any function, we might use f to the negative 1 as notation for the inverse. Now you have to be careful here because we've overloaded our notation. We're using notation that means different things in different situations. So this negative 1 is not supposed to be a regular exponent. We shouldn't be thinking about that as 1 over f. It's the reversal of f. Okay? So this is a standard shorthand notation for inverse functions, and it overuses the idea of an exponent. It overuses the idea of a superscript to stand in for something new. Okay? So now, let's think about this idea of combining something in its inverse to return the identity to figure out how we might find an inverse in a few different situations. So if f is a function and f to the negative 1 stands for the inverse of that function, what I want is I want to layer these together and I want to create the identity function. So I want to take f and I'm going to compose that with f inverse, and the result of that layer, that composition of f and its inverse, that should give me just the identity function. That should leave the input alone. So here, if you think about this composition in stages, you have the input, which you're putting into the f inverse. Then, what you're doing is you're changing that, okay? And then when you change that to the output of f inverse, f is bringing you back to x, okay? And this could happen in the other order. You could have f inverse of f of x, and that's, you've layered the function and its inverse in the other way, but you still want them to cancel out. So you would still want them to give you back the original input that you put into this composition. Okay? Now, I want to use this idea, an argument notation, to actually show you how you can figure out formulas for inverse functions if your original function is simple enough. All right? So let's define f and then find an inverse function using this idea. So let's say that f of x, we have a formula for it. Let's say it's 2x plus 1. All right? So there's a nice affine function. F of x is 2x plus 1. And what I'd like to do is I'd like to figure out what the inverse function would be. What's going to kind of cancel out all the operations of f. And I'm going to use this property to do it. I'm going to say that what I want f inverse to do is to, when I plug it into f, give me back just x. Okay? So the way that I'm going to figure this out is I want to kind of do some work, and at the end of the process, I want to have f inverse of x on one side of an equation and a formula for f inverse on the other side of the equation. That's the objective that I want to fulfill. If I can get this statement to look like this, then I'll have a formula for f inverse, and I'll be done. I'll know what the inverse is. Okay, so to do this, we just have to take advantage of argument notation. So if f of x is equal to 2x plus 1, then f of f inverse of x, that would be all the same stuff with f inverse plugged in. So this would be 2 times f inverse of x plus 1. Okay? And we want f and f inverse, when we combine them in this way, to give us just x. That's the identity function. So this should be equal to x. 2 times f inverse of x plus 1 is equal to x. Now I'm just going to use regular old algebra to solve this relationship for f inverse. I'm going to get f inverse of x by itself on one side of the equation. All right? So to do that, I could subtract 1 from both sides. So I get 2 times f inverse of x is equal to x minus 1. And then if I want to finish solving, I can divide by the coefficient here. So divide both sides of the equation by 2. If I divide the left side by 2, I get just f inverse. And if I divide the right hand side by 2, I get x minus 1 divided by 2. So that actually gives me a way to find a formula for f inverse given a formula for f. Okay? Let's do one more example of this, and then we'll look at some of the caveats and problems that come up when we try to handle or deal with inverses in general. Let's say that f of x is equal to 3 minus x divided by 2. Okay, so there's another kind of simple function that we might be dealing with. And we want to find its inverse. How do we find the inverse of this function? We say that f layered with f inverse, when we put those two things together, the result should be the identity function. That's the defining property of an inverse. So first we use argument notation to figure out what this is, and then we manipulate the result algebraically, to get a formula for f inverse. So if this is f of x, f of f inverse of x is going to be equal to 3 minus f inverse of x divided by 2. Okay, so using the property of this inverse function, we want this statement, 3 minus f inverse of x divided by 2 to be equal to x. Okay? Now, I'm just going to go ahead and I'm going to solve this equation for f inverse. I'm going to isolate it on one side of the equation. So multiply both sides by 2, giving me 3 minus f inverse of x is equal to 2x. And then I can rearrange this in a few different ways. I think what I would choose to do would be to add f inverse to both sides and then subtract 2x from both sides. So adding f inverse to both sides will move it from the left side of the equation to the right side of the equation. So I get f inverse of x. And then subtracting the 2x from both sides, the 3 we haven't changed, so that's there. We subtract the 2x from both sides, we get a minus 2x on the left. And this is now a formula for f inverse. Okay? So now, we've got f inverse. Let's just double check, kind of check our work here, and make sure that when we compose the functions in this way, the result is just x, that everything kind of cancels out the way that it's supposed to. All right, so let's use our formula for f inverse, and we'll layer the function in its inverse and make sure that x is the result. So here we're just checking our work. Right, so we have our f. Here's our f inverse that we just found. That's 3 minus 2x. There's our original function. So let's look at whether this equation is actually satisfied by this formula for f and this formula for f inverse. So let's look at f composed with f inverse. So we put f inverse inside as the input to this function. So we get f of f inverse should be equal to 3 minus the whole formula for f inverse. 3 minus 2x. And then this is all divided by 2 because f is all divided by 2. Now, if I distribute the negative sign, I get 3 minus 3 plus 2x over 2. And then if we combine like terms in the numerator, 3 minus 3 gives us 0. We're left with 2x over 2. The 2's cancel. That leaves us with just x, which is what we want. We want the f and the f inverse to kind of unravel one another so that the original input is all that's left.